Okay guys, this is Dr. Kell and I am recording a video here for you guys to learn about recursive notation. Hold on, I need to get this thing set up properly. So if y'all remember, we have done earlier in the semester we did what was called explicit notation, okay? So we have covered this type of material, okay? So hopefully you remember that when we were doing explicit formulas, we said, hey, fun for later, we're gonna do recursive formulas later. So now is that time, okay? So arithmetic sequences and geometric sequences. So we're gonna look at if we can tell if a sequence is an arithmetic sequence, a geometric sequence, or neither. And we're gonna learn to write the equation, okay? So a sequence is just a pattern of numbers. Okay, so it is a way that you can predict the outcome at a certain term, okay? So the term of a sequence is one number in the pattern. So arithmetic and geometric sequences are useful because we can predict, like, what is the thousandth number in this pattern going to be, and we don't have to sit there and go through calculating one at a time. We can just jump right to the gun and calculate what, like, the, you know, whatever number we're interested in. Okay, so an arithmetic sequence is in the form of, let me try to remember, a sub n is equal to d, hold on, let me just look it up really quick, make sure. Yeah, d times n plus what we're going to call a0, okay? So here is the deal. A0 is the initial value, okay? Like the 0th number in the sequence, okay? A sub n is like the current number, the current value you're calculating. So if you're looking for the 100th entry or the 10,000th entry or something like that, okay? N is the number of the value you're looking for. And then D is this thing called the common difference, okay? It is the difference between one value to the next, value. Okay, so what I want to kind of dive into here on the arithmetic sequences is that you should recognize when an equation is in this pattern, okay? This is, all this is y equals mx plus b, okay? B would be that initial value, okay? M is that common difference. And then x is the current number, okay? And then y would calculate that. So this is just a linear equation, okay? So we'll look at a couple examples of this. A geometric sequence is going to be, I'm going to do it in a different color. I'll do, what color? Green. Okay, so we have some demonic colors in here. So a geometric sequence is in the form that a sub n is equal to your a1 times r to the n minus 1. Okay, so now we have a different pattern, okay? So a1, again, is your first term, okay? So over here, this was like your 0th term, okay, or initial value. For a geometric sequence, A1 is your first term, and then R is your multiplier. Okay, so it is the ratio from one entry to the next, okay? So while the arithmetic sequence is in a linear form, the geometric sequence is in an exponential form. So we also have done a lot with exponential equations, okay? So here's what we're going to do. If we are going to tell if something is an arithmetic sequence, a geometric sequence, or perhaps neither, we want to see if there is a common difference, okay? So if there's a common difference, that's going to be addition or subtraction, okay? If there is a common ratio, that is going to be multiplication or division. Okay, so we're going to look at what the pattern is from one value to the next. And in these examples, we just want to determine if they're a geometric or if they are arithmetic. Okay, so let's go ahead and look here. So I'm going to zoom in here and let's look at what the pattern is. From 93 to 86, the change from there is we subtracted 7, okay? So now let's see if that is a common pattern. So let's just figure out what 86, the difference between 86 and 79 is. Oh, hey, again, we subtracted 7. For good measure, let's just go ahead and do one more. So from 79 to 72, yep, that's also, we're subtracting 7. So our common difference is -7. This one is arithmetic. This is a linear equation. Okay, so let's look at this one now. Let's figure out what is the pattern from one value to the next. So if I look at this first one, it looks like this was multiplied by 4. Okay, 3 times 4 is 12. And the next one, hey, it's also multiplied by 4. Okay, I'm just going to double check the next one. I can't do 48 times 4 in my head, unfortunately. Yep, it is. It's times 4. So this one's a geometric. This is an exponential, okay? This is like an exponential equation. And our common ratio is 4. Okay? All right. Let's go ahead and look at C. All right? So let's look at the pattern here. Well, from 1 to 4, I could look at it as though I'm multiplying by 4. I could also think of this as I'm adding 3. Okay, let's look from 4 to 9. Well, this would be like, I don't know, it doesn't really have a multiplier. And then what would I be adding? 5, okay? And then to 16, I don't know, that one doesn't really have a pattern either. So I can't remember if we did this already in a different unit. If we tried to figure out the pattern, but what this one actually turns out to be is we would look at the second, like we would look at what the difference is from one number to the next, and then we would do it again. So from 3 to 5 is 2. So from 5 to 7 is 2. So this one would actually be a quadratic. But for this purpose, we're going to say neither. Okay. Okay, next one. 1 more, 2 more, 3 more. Okay. So let's see. Is this a arithmetic, geometric, or neither? So I'm just going to look at what the pattern is from one number entry to the next. Okay. So from -10 to -12, we're subtracting 2. Looks like we're subtracting 2 again. But wait a second. Here we just subtracted 1. Here we just subtracted 3. This is also going to be a neither. It's not a consistent pattern, okay? So don't fall for it by looking just at like the first entry. Make sure you look further on, okay? So now what about E? So 27 to 9. What can you do here? Well, we could like divide by 3. 9 divided by 3 is 3. 3 divided by 3 is 1. So it looks like this is a geometric, and my r would equal 1 over 3. Okay, so dividing by 3 is the same thing as multiplying by 1/3. Okay, and then let's look over here. So from 2 to 8, well, this would be like adding 6 or multiplying by 4. From 8 to 30, what is that? We're adding 22. And I don't think there's a multiplier to go from 8 to 30 nicely. And then from 30 to 120, I don't see a specific pattern here, so I'm going to say that this one is a neither. Okay. Okay, so listen up, you guys. It is very, very, very important that when you guys are using this video to learn or to review, that you actually pause and do the U-tries. So at this point, please go ahead and do that. Okay, so hopefully you've paused and you tested this out. For G, I would say neither. For I, I'm going to say that this is a geometric sequence, and your multiplier, your common ratio, is 1/2. And then for H, this is an arithmetic sequence, and your common difference is -1.1. Okay, so let's go ahead and look at how we put this into the formula, okay? So what we're going to focus on today is looking specifically at these two boxes, okay? So we are going to look at the sequence notation and the for both the recursive and the explicit formulas, okay? I'm trying to remember what chapter we even did this in. I think some of this was last semester when we looked at like the function notation. So we're kind of building on something that we've kind of introduced to, but maybe not to this level. Okay, so when we're using sequence notation of recursive formulas, you want to find your initial value. Okay, that is something you want to find. Okay, you want to then find your common difference. Okay, and this right here, this n-1, it is the initial value minus 1. Okay, so this is kind of a weird idea. So this is like the number before the initial value. Okay, when I think of this, I usually like to think of it as like your 0th entry, okay? But it's kind of a weird concept. When we are looking at a pattern of numbers, we're not typically given the n-1 entry. Rather, we have to kind of figure that out. We have to go backwards and figure that out. Okay, so let's go ahead and look at some of these. So I think actually I just had to double check what lessons have already been done. And I think that our main objective today is actually just to use the sequence notation and the recursive formulas, okay? All right, so our objective is going to be to create an equation in this pattern, okay? Again, the point of doing this is that we can predict a certain value based on the value that came before it, okay? All right. Okay. And I actually want to correct myself with something I said a moment ago. This right here, this is actually not the initial value. That is the value before. Okay, so when we're doing a sequence notation, what we need to write is we need to write what is your starting value, and you need to figure out what is your common difference. And then these two things, a sub n and a sub n minus 1, they stay as like part of the formula, okay? So we need to figure out a specific thing there and a specific thing there. Okay, so let's go ahead and look here. Okay, so let's start at looking at what our pattern is here, okay? So from -9 to -6, it looks like I'm adding 3, adding 3, adding 3. So it looks to me like my common difference, my D, is 3, okay? So again, I'm not going to worry about explicit at this moment, okay? So I can put a 3 right here, okay? Now I need to find what is my first entry. Well, that's easy. Here I can just look at it. My first entry is this -9. So I'm going to say that A1 is -9, okay? Okay, so now to use the recursive formula to find the 11th entry is honestly a little bit of a pain. Using an explicit formula for this is much, much easier. But here's what we're going to do. I'm going to come back here and I'm going to look at this sequence. Okay, so this is my first, my second, my third, my fourth, my fifth entry. Okay, so if I want to find A of 11, I want to find the 11th entry. That means my 11th entry is going to be equal to A of 11 minus 1, or 10, A of 10 plus 3. Okay? Well, so now I need to go and figure out what A of 10 is. Well, A of 10 is going to be equal to A of 9 plus 3. And then A of 9 is going to be equal to A of 8 plus 3. And I'm going to keep going over here. A of 8 is going to be equal to A of 7. That's a 7 plus 3. A of 7 is equal to A of 6 plus 3. And then A of 6 is equal to A of 5 plus 3. Okay. So here's what I'm going to do. I know A of 5, right? Oopsies, wrong pen. A of 5 is this value. A5 is that value. Okay, it is 3. So I'm going to kind of like backtrack up, right? So if A5 is 3, then A6 is 3 plus 3. And then A7 is going to be 6 plus 3. Let's go ahead and write what it equals. So this is 6. I'm going to add 3. That's, excuse me. Yep, I'm adding 3. Okay, so for a second I thought I was subtracting 3. Okay, so this one's going to be 9. This one's going to be 12. This one's going to be 15. This one is going to be 18. And then A of 11, which is our outcome, is going to be 21. Okay, so that's the pattern. I think explicit is a lot easier to apply this pattern. But let's go ahead and look at this next example. So let's go ahead and try to find our common difference. Okay, so again, we're going to skip explicit for now. My A1 is that starting value is 47. Okay, so to go from 47 to 39, I am subtracting 8, and then that becomes my pattern if I look at that. So my common difference, my D, is -8. Okay. So I'm just going to write this in a more simplified way instead of actually finding A11. I'm going to say A11 is equal to A of 11 minus 1, or A10 minus 8. And then I can say here that A1, well, we know that A1 is 47. Okay, let's see if you guys can set up this part of the equation on these next 2 U tries. So pause the video and try to create this equation or this equation, and then we'll together try to find the specific entry. Okay, so for your recursive formula, you should write what your starting value was. For this example, it is 81. And then you're going to write the recursive formula that a sub n is equal to a sub n minus 1 plus 4, which is our common difference was 4. So if we want to go ahead and figure out the 11th entry, I'm going to start here with the highest number in the sequence that they gave me, which this is my 1, 2, 3, 4, fifth entry. So this is a sub 5, okay? So I'm just going to add 4 to this, however many, 6 times, in order to find my 11th entry. So I'm going to say 97, and I'm just going to add 4 times 6. Okay, so this is going to give me that a sub 11. It would be a10 plus 4, and in this case, a11 is 121. Okay, so let's go over here and look at example D. My common difference here is -2. I'm subtracting 2 every time in the pattern. So the formula that I'm looking for, I need to know my starting value, and I need to know my, oops, I wrote that wrong, it's supposed to be 2. I need to know my common difference. Okay, so this is a sub n minus 2. So a11 is again going to be equal to a10 minus 2. Okay, so if I look at this again, this is the 5th entry. Okay, so to get to the 11th entry, I'm going to need to subtract 2 from this 6 more times. Okay, so I'm going to take -11, and I'm just going to kind of tick down that sequence until I get to that point. And if you try to figure that out, you should see that the 11th entry is -23. Okay. All right, so let's look at how we can identify the arithmetic sequence from a graph. Okay, so we have this graph over here to the side. And if we look at this, this is actually a sequence. So I have numbers ticking up here on the x-axis. I have numbers increasing here on the y-axis, okay? So this is actually my A1, this is my A2, and so forth, okay? If I look at what is changing between each entry, I can see that we are subtracting 5, okay? So we're looking for something where my A1 is 45 and my common difference is -5. So let's see which of these we can identify. So these two, A and B, these are in explicit notation, okay? If you go back and look at your notes from explicit notation, you should see that A would be our answer in explicit notation. And in this example, I'm looking for where my A1 is 45 and my common difference is -5. So it looks to me like this would be example formula C. Okay. So let's see if we should do examples 4 and 5. So this is telling me to go from one type of formula, recursive formula, into the explicit formula. And this example is telling me to go from explicit into recursive. So if you guys remember, let's just do a quick review on the explicit formula. Our nth entry is equal to our initial value, our starting value, minus the common difference times n, okay? So in each of these cases, we actually know the same information from our explicit formula. Here I have my A1, and here I have my common difference. So I can kind of plug that in and rewrite the equation in a different form. So I'm going to say in explicit notation, this is going to be 17 minus, my common difference is 4 times n. Okay? So why don't you go ahead and pause and try that for example B. Okay, so example B should look something like this. This is my starting value minus 2 times n. Okay, example 5 is going the other way. Okay, we want to write this from explicit into recursive. So again, this is going to be my my A1. Okay, so I will say that A1 is equal to -5, and then this is going to be my D. Okay, so writing this in recursive formula, I'm going to say A sub n is equal to A sub n minus 1, and it'll be plus 3. Okay, so again, for recursive, I need to have a specific A1 and a specific D. In the same sense, for this one, my A1 is 11. I can see that my D is 40. So I'm going to say AN is equal to AN minus 1 plus 40. Okay, so so if we want to look at this in this concept here called function notation, let's just zoom back up here really quick. Function notation is the exact same thing, except for that instead of saying A with this little 1, we're going to say f of 1. Instead of saying A little n, we're going to say f of n, and so forth. Okay, so that's the only difference. It's just written in a little bit of a different way. It means the exact same thing. Okay, so where were we? Come back. Okay, so let's look at if we can write these in sequence and function notation really quick. Okay, I think our main goal today is just to look at this recursive notation, but let's go ahead and put it in function notation as well. Okay, so here I'm going to try to figure out what my common difference is. Okay, so see if you can figure this out on your own, but what I am seeing is that it's -5. I'm also looking at this and I'm seeing that my A1 is 7. So in recursive notation, I'm going to write out this formula, and that works. Okay, in function notation, I'm going to say my f of 1 is at 7, and now my f of n is equal to f of n minus 1 minus 5. Okay. The thing that's kind of like, in my opinion, a little bit annoying about recursive versus explicit is in order to use recursive notation, you kind of have to like tick up the chain. Rather, with explicit notation, you can just jump to whichever number you're trying to solve for, and it's kind of more convenient. Okay, so now we're going to go ahead and let me just double check that this is on my to-do list. Sequence and recursive notation. Okay, so yeah, so let's go ahead and look at it for the geometric sequences. Okay, so here's going to be the pattern. Okay, we're going to look and see what our pattern is. Okay, if it's not the same adding every time versus it is multiplying, then this is going to be a geometric sequence and is going to be written like an exponential function. Okay, so what we are going to do for a recursive notation of a geometric sequence is we need to identify that multiplier. This is a multiplier. Okay, and we also need to use this initial value, your starting value. Okay, so when we are doing your recursive notation, we're going to call this R in your recursive notation. Okay, A1 is the first entry. AN is like any, is the nth entry. Could be 100th, it could be 1,000th. And the A minus 1 is the one before N. Okay, so let's go ahead and see if we can use this, okay? Okay, so again, if we, okay, so when we are plugging this into the actual formula we're looking for, we are going to plug in a specific A minus 1. This is the first value. And then we are going to plug in a specific multiplier. Okay. Okay. So we're going to write the function for each exponential function or geometric sequence in both function and recursive notation. So we are going to go ahead and just put it in recursive notation. So let's figure out what our multiplier is, okay? So first of all, I can see here, this is my 0th value. That is not my A1. This would be my A0, okay? The function, when I'm writing it down, is looking for my A1. So this one is my A1, okay? So now let's go ahead. I can write that down. My A1 is 12. Okay, so let's look at what my multiplier is. It looks to me like we're multiplying by 2 every time, okay? So my multiplier is 2, okay? So the next part I'm going to write is in this pattern. I'm going to say A sub n is equal to 2 times A sub n minus 1, okay? So if I want to figure out my f of 7, what I would actually really want to do is have this in function notation. So in this case, we are just going to leave our answer like this, okay? So let's go ahead and look at in this other pattern. Do you see how the information is given here versus given here? In this example number 2, this first entry here, this is your A1, okay? So if I'm going to write my recursive formula, I'm going to write my A1 is 27. Okay, I'm now going to look at what is my multiplier. So to go from 27 to 9, it looks like I'm dividing by 3. Dividing by 3 is the same thing as multiplying by 1/3. Okay, so my common multiplier is 1/3. Okay, so my A sub n is equal to 1/3 times A sub n minus 1. Okay. Again, to evaluate using recursive is a little bit more of a process. I think that we went over that in function notation, so maybe go ahead and look back at your notes from those examples. How much more do we have here? Oh, we have a summary. What do we have? We have a lot of summary. Oh, this is a fun review. I think that we'll be doing this in class. Okay. Oh, this is a great review. Okay, so we just have a couple more examples here. So go ahead and pause and try examples 3, 4, and 5 and see what you can get. Okay, after trying these 3 problems, you should have seen, you should have come to these answers that you could write your recursive formula in this pattern for number 3, in this pattern for number 4, and your answer choices for example 5 would be both B and C. That would be both function and recursive notation. Okay, good job for the semester, guys. You're almost done with the whole semester. Woo!